Section 11.1, Inferences from Paired Samples. It says here we're going to jump right in and take a look at an example, but first just a little bit of a discussion about what's going on in Chapter 11. Back in Chapter 9, we did hypothesis tests involving means, and in some of those problems we were comparing the mean of one population to the mean of another. And the way those problems worked is we knew the mean in one population, which means we took a census, and in the other population we only had sample data. There might be some instances where that could be true, but it's more likely that if you were going to make a comparison like that, you wouldn't know the mean from either population, and so then you would have to take a sample from both populations and use those to make your comparison. And that's what we're going to be looking at in this chapter, is two populations with two samples. So there's two ways that can work with means, and one of them is called independent samples. And that's where you might go to your first population, take a sample of, I don't know, say size 34 and calculate a mean from that one. And then you go to your other population and you take an independent sample of, I don't know, say 37 people, and you get a mean from there, and then you compare those sample means and try and make your decision. So that's one way that these can be done, but a more powerful way to do it is if you have paired samples. So that's what we're going to be looking at in this section. In paired samples, every member from one sample is naturally paired to one of the members from another sample, and we'll talk about that as we go through this problem. So now let's go ahead and jump in and take a look at this example. A pharmaceutical company has developed a new drug that they feel will help people who suffer from insomnia get more sleep per night. They obtained a random sample of 18 patients who suffer from insomnia. They recorded the number of hours of sleep for the patients on two randomly selected nights. For one of the nights they were given a placebo, and on the other night they were given the drug, and the paired results are shown below. Okay, so just a little bit of discussion of the setup here. It says on one of the nights they were given the drug, the other night they were given the placebo. They shouldn't know what they were getting, right? Because the idea of a placebo is maybe you're getting the real thing. And the other thing hopefully they did is kind of randomize which night it was, so that it wasn't always the first night for everybody that they got the real sleeping pill versus the placebo. So it seems like we only have one sample here, a sample of 18 patients. And in a way that's true, but we're going to think of it as two samples. One sample of 18 people who got the placebo, and then another sample of 18 people who got the drug. So the placebo night, we'll consider that to be sample 1. And then the night they get the sleeping pill or the real drug, that's going to be considered sample 2. And then just because there's 18 people, this is carried over into more rows. So this isn't a third and fourth sample, it's just more of the placebo sample and more of the drug sample. Now they referred to this as a paired sample, and what that means is that there's a natural pairing between the numbers, and typically when these are lined up like this, the pairing will be the ones that are connected with each other right next to each other. So what we mean by these being paired is this isn't just a random person who got 5.5 hours sleep on a placebo and then a different random person who got 7.2 hours when they took the sleeping pill. This is the same person. Call him George or whatever, right? But George got 5.5 hours the night he took the placebo and 7.2 hours the night he got the drug. And every one of these is the same person. So that's what we mean by naturally paired. It's very natural to put this 4.6 with that 3.4 because they're both from Nancy or, whoever this patient happened to be. All right, so let's go ahead and start looking at how the hypothesis test works, beginning with their question for us. Does the data show at the 1% significance level that the drug will increase, on average, the number of hours of sleep per night for patients who take it? So the first thing that we always try to decide on these hypothesis tests is what type is it, and one of the main decisions we make is it about an average or about a proportion. We can see right here this is a test about an average. So we're going to want to have an HO and H1, the symbol mu. So what we would have done in the past in chapter 9 is we would have said mu equals something. And then we'd go read the problem and we would look for some number that was either claimed or old or some default or a comparison number to set mu equal to. But you can go back and reread this problem and you won't find any such number. And that's because we don't know the mean from either population. So in these, instead of setting the mean equal to a specific number, we call this one mu1 and we set it equal to mu2. And so what we're claiming there is that on average, people who take the placebo will get the same amount of sleep as those people who take the real drug. And we're doing the numbering to match up with the sample 1, sample 2. So this would be population 1, insomniacs who take the placebo, their average amount of sleep, and mu2 would be the population average for insomniacs who take the sleeping pill. Not just these 18 people, but if it was applied to the whole population. All right, so then for H1, we want to think about, are we going to put a not equal, a greater than, a less than, and kind of set up that whole left-tailed, right-tailed, two-tailed idea. So let's look at the wording again. We want to see if the drug will increase, on average, the number of hours of sleep per night for patients who take it. So when you hear that word increase, especially if you're kind of in your chapter 9 mindset, you would tend to just want to write a greater than. But it turns out, in this case, that would be incorrect, I believe, but we're going to investigate that together right now. When it says that we're going to get an increased amount of sleep, we have to pay attention to increase for who? The placebo group or the drug group? And it says the drug will increase the amount of sleep. So we're saying that the average will be bigger on the night they take the drug. Well, the night they take the drug is sample 2. And so we would want to say that mu2 is going to be the bigger one. So if mu2 is the bigger one, then our symbol is going to look like this. So it actually ends up saying mu1 is less than mu2. So when you hear a word like increase, decrease, that's a directional word, but you have to think carefully about which one are they saying is bigger, which one are they saying is smaller, and get the symbol correct with that. It won't automatically match like your instinct for how to translate it. So on your left-tailed or right-tailed test type words, don't just translate and plug it in, but think which one are they saying is bigger, which one are they saying is smaller, and make sure you get the symbol to match that. And then step 2, good old step 2, always giving us an easy step. Our significance level is 1%, so we can set alpha equal to 0.01, and then we can move on and start working on our test statistic. All right, so when we go to calculate the test statistic, there's a question that comes up, which is, what are we going to calculate averages for, right? We know we want to calculate some sample averages because we're doing a test about an average, but do we do the average for the night the person took the placebo? Do we do it for the night they took the drug? And the answer is no, we're going to do it for the differences between the two. So we're going to look at it one person at a time and see what kind of difference they had between the night when they took the placebo versus the night they took the drug. So I've already filled in the word there. Go ahead and make sure you do that. And I filled in these differences, but let me show you where those came from. So we take the first person, and on the night that they took the placebo, they slept 5.5 hours. And then we want to subtract how much sleep they got the night they took the sleeping pill drug, and that was 7.2. And then that difference is negative 1.7. And we do the same thing for the next couple people. So person 2, 5.6 on the placebo, 7.1 on the drug, and then person 3, 3.8 minus 4.9, and we get a difference of negative 1.1. So that's how I got those 3. Make sure you fill those in, and then all the rest are filled in for us. So before we go on to do more computation on our test statistic, I want us to think about what these differences mean. What does a negative mean? What does a positive mean? Are negatives good for us? Are positives good for us? So we're trying to show that the drug will increase on average the amount of sleep, right? Increase on average the amount of sleep that people got. So is a negative good or bad for us? Well, how do we get a negative? When the person slept 5.5 on the placebo and 7.2 on the drug. So that was more sleep the night they took the drug, which is good for trying to show the drug increases sleep. And when you do the subtraction, you get a negative. So a negative actually supports the idea that sleep is increasing. And then that also makes sense because the negative is to the left of 0, and according to that symbol in H1, we're doing a left-tailed test. So ideally for the drug, you just have negatives all the way down this column, meaning that everybody who took the sleeping pill slept more that night than the night they took the placebo. But if you go down this list, that's not quite true. Here's a positive 1.2, and that's somebody who slept 4.6 hours the night they took the placebo and only 3.4 the night they took the drug. There's a temptation when you see that to say, okay, the drug is working for most of these people, but it doesn't work for that person. Well, we can't really say that. We don't know that the drug doesn't work for them. We know they slept less the night they took the drug, but there could be other factors, right? Maybe the night they took the drug, they had a big meeting at work the next day that they were stressed about and couldn't stop thinking about, and it made it hard for them to fall asleep. Whereas maybe the night they took the placebo, they had done a lot of exercise that day and were just physically exhausted, and they fell asleep a little bit quicker and easier. So when you see that difference, maybe it was the drug that caused it, maybe it was other factors. But this is kind of randomly set up for all the people, so if most of the time the drug is working for people, meaning that most of the time they take the drug, they get more sleep, then there's a good chance that the drug is the reason for that sleep. All right, so we're going to want to move on and now use this column of differences to calculate our test statistic. So we've switched from 2 samples down to 1, and when we do that, we've kind of taken ourselves back to chapter 9 where we were doing one sample test on means. So I want to do a quick review of chapter 9, and then we'll see how we adjust that to section 11.1. So let's bring in a piece of scratch paper and let's think about what we did back in chapter 9. Back there we were doing a t-test when we were working with means, and our test statistic t was x bar minus mu 0 divided by s over root n, where x bar was our sample mean, mu 0 was the claimed mean from h0, s was our sample standard deviation, and n was our sample size. So in 11.1 we're going to model our test statistic off of that, but we're going to make some changes. First of all, we will reserve our right to figure out if that's a t or something else as we see the formula come together. But when we go to put this sample mean in, if we write x bar, that's going to be a little confusing. Is that the mean for the placebo? Is that the mean for the drug? And no, it's the mean for the differences. So how do we want to make that clear? What we're going to do is we're going to put a d bar there to show that it's the average of the sample average with a bar of the differences. We'll leave the subtraction piece for a moment, go down to the bottom. Same problem with s. If we put s, that's a sample standard deviation, but is that for this sample? This sample? No, it's for the sample differences. So what we do in our formula is we call that s with a subscript of d just to emphasize that it's for the differences. And then we put the square root of n, and there's no need for a subscript there because all 3 of the samples were the same on paired. That's always true. So sample 1 is the same size as sample 2 is the same as the number of differences. All right, so because we're using S right here, this is still going to be a t-score like it was back in chapter 9. The one piece we still have to deal with is what's going to go here. So right here, this would have been the number from H0, but thinking in terms of chapter 10 too, this is always what we would put if HO was true. What would we expect to see if HO was true? So here's our here's our average in the sample. What would we expect the average to be if HO is true? So here's our differences in the sample. What we want here is what we expect for the average of those distances or differences if HO is true. Well, if HO is true, then mu1 equals mu2. There's no difference. If HO is true, there's no difference between the effect of the placebo and the effect of the actual sleeping pill. And if there's no difference, that would be the same as saying the difference is 0. So when we do these tests in 11.1, we're always going to have HO say that mu1 equals mu2, which means this will always be a difference of 0 if HO is true. And when you subtract 0, nothing really happens. So when we write our formula, we will just leave that part off and say our test statistic is d bar divided by s of the d's divided by the square root of the sample size. All right, so let's bring that into our notes page and say that's our test statistic is going to be t equals d bar divided by the s of the d's divided by the square root of the n. So what does that mean? It means we need to find d bar and we need to find sd. We already know our sample size is 18. And once we find those things, we can plug them in and we can start doing a hypothesis test that is very similar to what we did in chapter 9. So we want to get the mean and standard deviation for this column. And one way to do that would be to just enter all this data in. But one of the things that's worrisome about that is it's very easy at some point to either put a negative where you shouldn't, like maybe on this one, because you're doing so many negatives you accidentally type a negative when you shouldn't, or maybe you forget a negative. And the way we're going to check to see if we've entered our data right on the calculator is look at the sum of the d squareds, or the sum of these numbers squared. And if we forget the sign or put a sign when we shouldn't, because of the squaring, we won't notice that. So what we should do instead, and let me just kind of describe that here, is we should put these data values in L1, we should put these data values for sample 2 into L2, and then for L3, we should let that be L1 minus L2, and that'll create these differences for us, and the negatives will be there if they're supposed to and not if they shouldn't, and we don't have to worry about forgetting them. We might still make a typo in one of these columns, but if we do, it won't just mess up the sign, it'll mess up the number, and then we would notice when we check that piece. All right, so let me show you that on the calculator. So I'm going to go in there, and I would normally enter the data, but I already entered that before I got started, so I'm just going to show you this part. Highlight the L3 and let that equal L1 minus L2, and you see that right here. And when I press enter, that should create this entire column of differences. And we can check those first three that we did ourselves. So negative 1.7, negative 1.5, negative 1.1, and then the rest seem to be correct as well. All right, so I would recommend that you pause the video and you try and replicate that real quick for yourself so that you feel comfortable with it in homework and any quizzes we might have. All right, so next I'm going to go ahead and get the average and standard deviation for this column. So I'm going to hit the stat key again, go over to calc. I'm going to do one variable statistics, and my data is an L3. Typically in the past we were doing L1, but our differences are in L3, so that's what we want to do here. And they call it X bar, but we know that's for our difference column, so I'm going to call it D bar. It's good to put lots of decimal places when you're doing a hypothesis test, so I'll put negative 1.1667. And for S, that's right here. They call it SX, but again, these are differences, so that's approximately 1.1757. Remember, on standard deviations, we should put at least 5 digits, so 1, 2, 3, 4, 5. And actually, I probably shouldn't have written any of that down until I made sure my data entry was correct. And here it says the sum of the x squareds is 48. And here it says the sum of the d squareds is 48, so that's a nice check that all the data was entered into the calculator correctly. All right, so now we can go ahead and plug into our formula for our test statistic, our d bar, negative 1.1667 minus 0, which we don't need to write, divided by the s, 1.1757, and divide that by the square root of our sample size. We can note that here too. There was 18 data values. And we can go to the calculator. Typically when you do z-scores, t-scores, there's a subtraction in the top, so you need parentheses around it. You don't have that here, so you don't need the parentheses. If you put minus 0, you would need them, but we can just leave that off. But because there's two numbers in the denominator, we will need parentheses around that on the calculator, so make sure you do that. And make sure you're giving that a try along with me so that you're comfortable putting that in. So notice no parentheses around the top because it was just a single number. Open parenthesis around the denominator. I closed the parenthesis for the square root and closed it for the denominator as well. And I get a t-score of negative 4.210. And I think we should just pause for a moment there and think, is that good for us? Well, whose side are we on? We're on H1 side, and we're doing a left-tailed test. If HO was true, we would have expected this average difference to be around 0. But we're getting negative 4.210, which is way to the left of 0, so that seems like a good sign. If I had to make a decision right now just based on this, I would say we're probably going to reject HO because we're doing a left-tailed test, and we got a test statistic that was over 4 student deviations to the left, and it would be very surprising if such a big difference was just due to random variation. But we will check to see how likely or unlikely that is when we do our p-value on the next page. All right, so the p-value step on this is pretty straightforward. Our test statistic was a t, so we're going to draw a t-curve, which is bell-shaped. So I'll do that. With t-curves, you want to think about the df, and our df on this is just like it was for test of the mean back in chapter 9. It's n minus 1, so that would be 18 minus 1, which is 17. And then we have 0 in the middle, representing that idea of no difference. And then we put our test statistic on from the previous page. That was negative 4.210. And then it's a left-tailed test. Always check that against H1. Don't just say it's left-tailed because we landed on the left. It's left-tailed because we had a less than in H1. And then because it's left-tailed, we want the area to the left, which is this part out here, which isn't as big as I just made it look because we're way out there where the area is flattening out, so I expect that to be a very small p-value. So my p-value is equal to whatever that little area is right there, and it's a t-score, so we'll do t-CDF. We're going off forever to the left, so negative infinity is my left boundary, negative 4.210 is my right boundary, and I have 17 degrees of freedom. And I'm expecting the answer to be almost nothing because there's not much visible area on that picture. So into the distribution menu, find our t-CDF function, go from negative infinity to negative 4.210 with 17 degrees of freedom. Expecting a small number and getting 2.943, which is impossible for an area. So we look over here, see the e-4 and go, okay, so we need to move our decimal place 4 spots to the left, which means that 2 would be in the 4th spot. And if I'm going to stop there, which is what I would normally do, 4 decimal places, I better look at the next digit, which is a 9, would cause that 2 to round up to a 3. All right, so there's my p-value, very much like what we did in Chapter 9. And step 5 is now to make our decision. Are we going to reject or not reject? Well, when we saw this test statistic land way out to the left on our left-held test, we should have seen that as strong evidence against HO and felt like we would reject it. But before we would reject HO, we would think about the risk of a type 1 error. Very, very low. Certainly lower than alpha. We had kind of a small alpha on this problem, 0.01. But this is 0.00 in those first 2 spots. So we can go ahead and reject HO because our risk of a type 1 error is very small, making it an acceptable risk. And so then stating our conclusion in words, there is enough evidence at the 1% significance level to show that the drug will increase, on average, the number of hours of sleep per night for patients who take it. All right, so now moving on to part B, comment on the requirements. This was a test about an average, so for those, we usually want to think about our sample size. Our sample size was 18, and when you're thinking about averages back in Chapter 9, you'd probably start off saying something like, because my sample size of 18 is bigger than or equal to 15, but smaller than 30, that makes it a medium-sized sample. So we would usually say something like, well, so we hope that our population is not severely skewed. However, what population are we talking about? The population of sleep people would get when they took a placebo, population of amount of sleep insomniacs would take when they took the sleeping pill, and nope, it's neither of those. It's the population differences between those. And since there's 3 things it can be, we can't get away with just saying we hope the population is not severely skewed. We have to say we hope that the sleep differences in the population are not severely skewed so that people know which of those columns we're talking about. All right, so because n is 18, in between the 15 and 30, we hope that the sleep differences in the population are not severely skewed. And we're hoping that so that D bar will be normally distributed. Because if D bar is normally distributed, then our t-score will have the t distribution and our p-value will be an accurate calculation. All right, so now let's go ahead and summarize the procedure that we just went through. So this is the procedure for performing the paired t-test for 2 population means from dependent samples. So we're not looking at independent samples in this section. That's section 11.2. That would be where we don't have pairing. So we're only doing this process if we have paired data. So that line is listed as a requirement, but it's really more about choosing the procedure. Should we be doing the paired t-test from here or the type of test that comes in the next section? And then the second one is the real requirement for the D bar to be normally distributed. The easiest thing would be if your sample size was large. If n is greater than or equal to 30, D bar would be normally distributed no matter what kind of population differences have as their shape. And then if the differences in the population are normal, that would be great for any sample size. So that's what we need when we have a small size sample. But when we're in this 15 to 30 range, like we were right up there, then we need our population differences to not be severely skewed. So depending on our sample size, we'll be looking at either A, B, or C there. And then we'll want to determine, for the procedure, determine HO and H1. And you just have to remember HO every single time is going to look exactly like this, because there's no number to plug in on these type of problems. We don't know the population mean from either group, so we're always going to have a mu1 and a mu2, and HO always has a quality in it. And then just the only thing to say for H1 is be careful, because remember, sometimes we have a word like increase that sounds like a greater than, but when you think about which one is the bigger one, sometimes you end up writing a less than symbol in your H1. So just be careful and thoughtful when you write that down. Step 2, decide on a significance level alpha. Step 3, calculate your test statistic. It's a t-score, so use 3 decimal places, and there's the formula we talked about, d bar divided by the s of the d's divided by the square root of n. In some of the problems, you'll have to calculate d bar and s of d like we did in this example. Sometimes they'll be given, like in the next example. So find the p-value using TCDF. Make sure you calculate your df using the sample size minus 1 like we did back in chapter 9. Reject HO or do not reject HO, and then state your conclusion of the test in words, talking about evidence and the application as you do that. All right, back in chapter 9, when we were doing our hypothesis test for means and proportions, that was right after having done chapter 8, where we were doing confidence intervals for the means and the proportions. And just like in those 2 chapters, when we do the hypothesis test for the paired data here, we could also do a confidence interval for the difference in the means for the paired data. So we're going to go ahead and look at the procedure for that and an example for that as well, just following up doing the confidence interval for the placebo and sleeping pill example that we just finished up. So the procedure here is for calculating a paired t-interval for the differences between 2 population means. So we're not doing an interval for mu or for p, but for the difference between mu1 minus mu2. So this is what we're trying to get a reasonable range for. And we're doing that for dependent samples, and by dependent what we mean is not independent, and what we really mean by that is they're paired. So the samples have to be paired data, and you still need the same sort of requirements for small, medium, and large sample that we talked about in the hypothesis test. Exactly the same list. So depending on whether you're large, medium, or small, that affects what you need for your population, if anything. So the steps: calculate your paired differences d from the sample, if that's not already been done for you, and calculate the mean and standard deviation of the sample differences if they're not given. So again, in some of the problems, like the one we just finished, we'll have to find the d's, enter those into the calculator, and get our d bar and our SD. But in a lot of the problems you do, it'll just tell you we took a sample and here's our d bar and here's our s of d. So that'll give you a head start on those. And then when you do confidence intervals, you need a t-score in the formula, but that t-score isn't the same t-score from the hypothesis test. It's one that depends on your confidence level. So draw a picture, put the confidence level they want in the middle, think about the area on the tails, and find the t-star that goes with that using n-1 degrees of freedom, and we'll look at an example of that in just a moment. And then your confidence interval for the difference between the population means is given by d bar plus or minus t star times s over root n. If you were to look back in chapter 9, this was x bar plus or minus t star times s over root n. Almost identical. It's just we're doing it for the average difference instead of just the average of a single sample. All right, so thinking back to that one we just did about the sleeping pill and the placebo, there was a d bar of negative 1.1667. The standard deviation of those differences was 1.1757, and our sample size was 18. So they want us to compute a 98% confidence interval for the difference in the mean number of hours of sleep with and without the drug, and without the drug meaning with the placebo. All right, so when we do that 98% confidence interval for a difference in the mean, right, difference in means, we're going to use this formula. So we're going to want to do d bar plus or minus t star times sd over root n. So what pieces do we know? We know d bar, we know sd, we know n is 18, and then there's a real temptation, though it's a bad idea, there's a real temptation to say, and we also know t, negative 4.210 from the hypothesis test that we did. However, That is not T star. T star is supposed to be connected with this 98% confidence level. So what we need to do is draw a picture of a T distribution, which should be bell-shaped. That's not a very good bell shape, but it'll do. And think about your DF, which is 17. And then you have 0 in the middle, and you think about how much area is in the middle. 98%. So if there's 98% in the middle, that's 2% left over. Cut that in half, and you'd have 1% on the right and 1% over here on the left. Think about adding all those up. Make sure it adds up to 1 or 100%. And then what we want to know is, what is the T star if you have 17 degrees of freedom and an area in the right tail of 0.01? So you could use your calculator and inverse T for that, but it's easier just to get your T table from your formula sheet. 0.01 is the area in the tail. Drop down until you get 18 degrees of freedom. 17 degrees of freedom, n minus 1. So T of 0.01, 17 degrees of freedom looks like 2.567 is our T star. All right, and then we want to just go ahead and start plugging all the numbers in. So D bar, negative 1.1667. So what does that number tell us all by itself? It means that in the sample, on average, people who took the drug slept 1.1667 hours per night longer than people who took the placebo. So we see the drug seem to have worked in our sample. However, it's a random sample of only 18 things out of a population of many insomniacs and many nights of possible sleep. So we have no faith that this is the right answer for the entire population, so we have to give ourselves some margin for error. And if we want to be 98% confident in our answer, we have to go out 2.567 student deviations on both sides, and we want to multiply that by S divided by root n, where S was 1.1757 divided by the square root of 18. And this piece right here, the plus or minus piece, is going to give us our margin of error for this problem. So negative 1.1667 plus or minus, and let's calculate that margin of error now. So 2.567 times 1.1757 divided by the square root of 18. And since we have 1, 2, 3, 4 decimals on this, we'll put 4 decimals on our margin of error, so 0.711, and it's a 3 followed by a 5, so we'll round that up to a 4. And then we'll do subtraction to get the left side. So negative 1.1667 minus 0.7114 is negative 1.8781. And then on the other side we'll do addition. Negative 0.4553. And then we want to write out front, what is this that we found a confidence interval for? What is it that we're 98% confident lies in between these two boundaries? And when I ask people this in class, a lot of times they'll say it's the mean, and so then I guess I would write mu, right? But if I wrote mu, what is that? Mu for the placebo, mu for the drug? And how is the average amount of sleep negative anyways, right? So this is not either of these. In fact, it told us back up here what this was for. It was for the difference between mu1 and mu2. So it's the difference between mu1 and mu2 that I'm 98% confident lies in between those two boundaries somewhere. All right, and now for what is probably the trickiest part in this section, interpreting that interval in terms of the application. So interpreting confidence intervals back in chapter 8 was pretty easy. We would just get into some sort of autopilot sort of thing. I'm 98% confident that the true mean of whatever is somewhere between this many and this many pounds or days or weeks or feet or whatever. But it's a little harder here. We could try it like that. We could say I'm 98% confident that the difference between the mean amount of sleep on the placebo and the mean amount of sleep on the drug in the population will be somewhere between negative 1.8781 and negative 0.553. So that's the kind of interpretation we gave before, but the problem is people aren't going to understand what we're saying. When we say the difference is negative, it's very confusing. We're talking about sleep and negative numbers. So we have to think about that and put it into a better interpretation, one where we're doing all the hard work and thinking for the person who's going to be reading our answer. So this entire range is negative. So what does it mean for a subtraction to come out negative. There's two things you could say. That means the first number is smaller than the second. That's how you get a negative when you subtract. Or the second number is larger than the first. That's how you get a negative when you subtract. You can do it from either point of view. Most people, when I ask them when do subtractions come out negative, they'll say when the second number is bigger. So I'm going to take this from that point of view. I'm going to say that a negative 1.8781 means that mu2 is bigger than mu1 by 1.8781 hours. And that negative 0.4553 means that mu2 is bigger than mu1 by 0.4553 hours. And then I'm going to think about, but what are these things? Mu2 is the mean amount of sleep people would get on a night when they took this drug. Mu1 is the mean amount of sleep people would get on a night where they took the placebo. So let me try it in words and then I'll try and write it down. I'm 98% confident that the true mean amount of sleep people would get the night they took this drug is somewhere between 0.4553 hours and 1.8781 hours more than what the average would be if they took a placebo. All right, let me write that down. So starting off with, we are 98% confident. That's the easy part. And then let's put mu2 into words. That the true mean amount of sleep people would get when they took this drug is somewhere between, and when I do a between, I always want to do the smaller number first and the bigger number second. With the negatives on, this is the bigger number, but I'm taking the negative off in symbols and I'm putting it into the words. So let me find my place again. So we're 98% confident the true mean amount of sleep people would get when they take this drug is somewhere between 0.4553 hours and 1.8781 hours more than the average would be, let's say the average sleep would be if they took a placebo instead. So what happened to the negative, right? The negative showed up in the phrase more than. If a subtraction comes out negative, it means the amount of sleep here was greater than that amount of sleep, and so that's why I'm saying more than for the night they took the drug, which was population 2, compared to the placebo, which was population 1. And by the way, I'm saying that they will get when they take, like in the future. And you might be thinking, but they already took the drug. We already have seen the results. But that was just for a sample. We're trying to say what would happen if you applied this to the big population of insomniacs. Like, does the drug help? And we're saying, yeah, it looks like they'd get somewhere between a half hour to almost 2 hours more per night on average if they took that sleeping pill as opposed to if we gave them a placebo. All right, and then the final piece here, which I think is actually easier than the interpretation, explain how the interval in part B, and actually that should be the interval in part A, so let me fix that right here, agrees with the decision we reached in part A of the test. So that was on the previous page. All right, so when I do these, I always like to start off with the hypothesis test, and we don't know for sure that this difference is in there, but we're 98% confident. So I'm going to start this sentence off with the word if. So if mu1 minus mu2 is an element of that range from negative 1.8781 to negative 0.4553, then what does that mean? Well, the first thing it means is that this difference must be negative. And the way we say that a difference is negative in math is to say the difference is less than 0. So that implies that mu1 minus mu2 is less than 0. And we can do a little bit of algebra and add mu2 to both sides of that and say that implies that mu1 is less than mu2. And if you think about it, that was our h1. So that implies h1, which said mu1 is less than mu2, is true, and that ho, which said that mu1 was equal to mu2, is false. And if we are confident, 98% confident in this, so at least 98% confident that HO is false, what should we do with a false claim? What should we do with a claim we are confident is false? We should reject that claim. So I would reject HO. So this is what I always like to do for this type of question, is just start off with a confidence interval and think about what that means in terms of whether HO or H1 is the true claim. And once I sort out whether HO is true or false, I can think about whether I should reject it or not. And then at the end, I want to go back and say, is that really what we did? So we go back to that previous page, bring that in here, and we did in fact reject HO, so we have agreement here. All right, so it turns out that this case is the easy one, when both of these signs are the same. It's a little trickier when you have one of each. So let's go ahead and take a look at one more example where we examine what happens when you don't reject HO and what happens when you have one of each sign in your confidence interval. A large timeshare company in Hawaii noticed that they seemed to be selling fewer units than in the past. At the end of a slow summer month, the company decided to test out a new incentive plan. They offered bonuses to any of their sales associates who produced an increase in sales the following month. After the end of the first incentive month, they randomly selected the records for 31 of their sales associates and compared the number of units sold in the month prior to the plan, which we'll refer to as population 1, to the number of units that are sold during the first month of the plan, and we'll refer to that as population 2. The paired sample produced the following statistics. So the fact that they refer to this as a paired sample means that we're using the records from the same 31 employees, both the month before the plan started and the month after, and that way we can link the sales, compare how a specific person did the month before to the month after. Now, it's possible that they could have showed us all the data, but instead they just gave us a summary that there was 31 people involved in the sample, that the average difference was negative 0.226, and that the standard deviation of those differences was 1.8203, and the units on that would be number of units sold, not dollars, because it's talking about the number of units sold up here in the problem. All right, so what do they want us to do with that information? Does the data provide enough evidence at the 5% significance level to show that the average number of units sold for the sales associates was higher the month after the incentive plan was enacted than it was the month before the plan was enacted? And to me that makes sense that they're looking into that because they've put in this bonus plan to try and increase sales, so now they want to see was it in fact higher. And then the other thing that kind of catches my attention is they want to see if the average number of units was higher. So that the fact that they're looking into the average says this is a test about means, so we're going to be writing mu rather than p as we go through and do the problem. Now because it's a hypothesis test, I expect to do 6 steps, and step 1 would be to write down h0 and h1. And as we just said, this is a claim about averages or means. And in this type of test, we always say that mu1 equals mu2, where mu1 would be the mean for population 1 and mu2 would be the mean for population 2. So HO is saying basically that the average sales before the incentive plan is the same as the average sales after. But that's not what we're trying to show. We're trying to show that the average sales were higher after they put the plan in. There's a temptation when you hear the word higher to put a greater than right here, but that would actually be a mistake. We're comparing mu1 and mu2, and we want the plan to be higher the month after the incentive plan. Well, the month after the plan, or during that first month of the plan, that's population 2. So this is the one that we want to be higher, so that means we want this one to be smaller than that one. So the word is higher. It might look like I've translated it wrong at first by putting a less than, but this is the sales, the average sales, the first month of the incentive plan. This is before the plan. So this reads that the sales before the plan was enacted, on average, were less than the sales after, or if you turn it around, the sales after were bigger than the sales before the incentive plan was enacted. So that's step one. Always be careful with that word and really carefully think about which way it should go. Don't just read the word quickly and throw a symbol on. Think about which one is higher than which. And then step two, decide on a significance level. So on this problem they tell us to use a 5% significance level, so I'll write that alpha is equal to 0.05, and that would be the setup phase of this test. So this is supposed to be done actually before they even collect data or choose their 31 employees that they're going to use as their data set. And then in step three, we're supposed to go out and gather and weigh the evidence. And they've already done the gathering and even done a lot of the computations for us, but we still need to compute the test statistic. And for this type of test, we're going to use a t-score. The numerator is the average difference in our sample, and we divide that by the standard deviation, which would be the standard deviation of the differences divided by the square root of n. So in this case, the average difference was negative 0.226, and that's divided by s, which is 1.8203, and that's going to be divided by the square root of 31. Now, before I enter this in the calculator, I want to think a little bit about what this means that d bar is negative. So if the average difference is negative, we have to remember what order the differences are going to be taken. For each person, we're looking at what they did before the incentive and then after. And if these differences right here are coming from doing before minus after, then if we get a negative for that, it means that after was a bigger number. So this means that in our sample at least, people were selling a little bit more than or almost a quarter of a unit more than they were before the plan. So that's given me a little bit of evidence that maybe this incentive plan is working, but I don't know if that difference is big enough to rule out random variation, so I want to continue calculating this test statistic in the calculator and see not just did I land to the left, which would be good for H1, but did I land far enough to the left. When I put this in the calculator, I do need parentheses around the denominator, so I'm just going to show those in red so we don't forget to put them. And then let's go ahead and bring the calculator in and see what we get for that test statistic. So in the numerator we have negative 0.226. We're going to divide that by 1.8203 divided by the square root of 31. Again, remembering parentheses around the denominator so that this division right here happens before the overall division in the fraction. And when I do that, I get a test statistic of negative 0.691, which we should know from previous hypothesis tests is kind of a small difference. So at this point, I feel like it's very likely I'm going to end up not rejecting HO, because in order to reject my claim, I need to see a big difference between what I saw in my sample and what I would have expected to see if HO is true. And just a reminder, if HO was true, then the sales would have been the same before and after, and so what we would have expected to see would have been a 0. So if HO is true, then I expected that. And then this is what I actually observed. So kind of thinking about that in terms of chapter 10, where you look at something you observed from your sample and what you would expected to see if HO is true. We don't bother putting the minus 0 in the calculator because it doesn't change the numbers at all. But the difference between what we observed and what we expected is less than 1 standard deviation, so that's not very strong evidence against HO. So I feel like I'm probably going to reject, but anytime I reject HO, I'm taking a risk of making a type 1 error. And before I would take a risk of a type 1 error, I'd like to know how big it is. So I'm going to go ahead and calculate my p-value in step 4, just like we normally would. This is a t, so that's a bell-shaped curve. And on t-curves, the df is always something you have to consider. And we're back to the idea that the df is n minus 1, so if my sample size is 31, then the df is going to be 30, just subtracting 1 from that sample size. And then I put 0 on, representing what I expected to see if HO was true, and then I'd put my test statistic, this negative 0.691, which would be over here on the left, and then I have to ask myself that question, is it left-tailed, right-tailed, or two-tailed, and that comes from looking at H1. It's a left-tailed test, so I would shade this area to the left, and whatever that area is, that's my p-value. So to find that area right there, I would do TCDF from the left boundary, which there is not one, so negative infinity, to the right boundary, negative 0.691, and because it's a t-curve, I also need the df, which should be 30. And when I do that, I'll be finding the p-value. So let's bring in the calculator and see how big our p-value is. I expect this to be kind of a big number because the evidence is weak, and if I were to reject HO with weak evidence, the risk of that being a mistake should be kind of high. So TCDF from negative alpha infinity to negative 0.691 to 30, or with 30 degrees of freedom. And I put that in, I do get kind of a big value there, 0.2474. So there's my p-value. It's always my goal going into a hypothesis test to reject HO, but in this case the difference wasn't very big, less than 1 standard deviation apart between what I observed in my sample and what I would have expected if HO is true. So if I were to reject here, there'd be a high risk of making a type 1 error. Or another way of looking at it would be to say, if HO is true, would we end up getting 0 for our differences? Probably not. We usually don't observe exactly what we expect to see. So if HO is true, could we have got a difference like this? And the answer is yes. There's like a 24.74% chance that if HO is true, we would have seen differences like this in the sales before and after anyways, just due to random variation. So it's kind of reasonable to believe that HO could be true and we'd get a result like that. And if it looks reasonable that HO could be true, then we don't want to reject it. So 2 reasons to say why we're not rejecting HO right here. One of them would be kind of the standard, it's too risky, just saying that the p-value is assessing the risk of a type 1 error. And then also just because this difference is small enough that it's plausible to see a difference like that if HO is true. So HO seems kind of reasonable. So we didn't reject HO, so that means the data did not provide enough evidence. We wanted to reject. If we had enough evidence, we would have. So the data did not provide enough evidence at the 5% significance level to show that the true mean number of units sold for the sales associates was higher the month after the incentive plan was enacted than it was the month before the plan was enacted. So it may seem again a little strange to use the word higher when H1 has a less than, but remember that I'm saying we didn't have enough evidence to show that the mean number of units was higher after the plan was enacted than it was before. This is after, that's before, so it does make sense to say higher. We were trying to show this one was higher than that one. Alright, so those are our standard 6 steps, and then we'll look at some follow-ups on the next page. Alright, moving on to the follow-up questions. They want us to comment on the requirements. Well, in this case we fall into our easiest scenario because our sample size n was 31, and that's greater than or equal to 30. And as long as you have a sample size over 30, then your requirements are met. And what that's really doing for you when your sample size is over 30 is it's ensuring you that the values of d bar are going to be approximately normally distributed. And that means that the requirements have been met. And that's true regardless of the distribution of the sales differences in the population. So you might remember that when our sample size was small, under 15, we were saying that we hoped that the distribution of the sales differences in the population would have been normally distributed, or if our sample size had been something like 18 in the 15 to 30 range, we would have been saying that we hoped that the distribution of the sales differences in the population were not severely skewed. But we don't have to worry about any of those. When our sample size gets up over 30, the d-bar should be normal no matter what the differences were like in the population. So that again is the kind of the best scenario, is to have that sample size that's over 30, especially if whoever wrote the problem was kind enough to calculate the d-bar and s for us. Keep in mind that if they had not done that, we'd be entering 31 before sales figures into L1 and 31 after figures into L2, and then be calculating all those differences ourselves. So a bigger sample can actually be a pain, but in this case that pain was done and felt by somebody else. Alright, let's move on to the confidence interval. They want us to compute a 90% confidence interval for the difference in average sales for all the personnel the month before the incentive plan and the month after the plan. So this is again about an average, and our formula in this section for doing that is to take the difference in the sample, or take the average of the sample differences, and that's probably not equal to the difference in the population mean, so we want to give ourselves some margin for error. So we'll add and subtract t standard deviations of d bar, which would be the standard deviation of d divided by the square root of the sample size. So if you look back at the information that was given to us on the previous page, they had already given us the values of n, d bar, and s, so the only one that remains is t star. Just a reminder, there's some temptation to use this, but the test statistic from your hypothesis test is not t star, because t star is supposed to be connected to this 90% confidence interval. So if we want to get that 90% confidence interval figured in there, then we should draw a picture of a bell-shaped curve. And again, just a reminder, this is a t-curve with a df of 30, and then show that 90% confidence as an area of 0.90 in the center of our curve, and then think about if there's 90% in the middle, that means there's 10% left over, but we have to split that 10% among the two sides, so that would be 0.05 on each side. And then we would consider, alright, so what is the t star that has an area of 0.05 to its right when the df is 30? And the easiest way to answer that is to go to our chart, look at t of 0.05, drop down until we get the row with 30 degrees of freedom, and there's the t star we want. Again, in the 30 degrees of freedom row and the t of 0.05 column. So 1.697 is our t star. And now we have all four pieces. So I guess we'll just start plugging them in actually right here. So let's see, pulling that other page in one more time. We had our d bar negative 0.226. That was the average difference in our sample, but we don't expect that to be exactly right. So we're going to give ourselves some margin for error. And what we just figured out is we need to give ourselves 1.697 standard deviations worth of room for error. And that will be s over root n, where s is 1.8203 and n is 31. And it's the square root of n that we want right there. Alright, so we have all those numbers from that page, so we'll get that out of the way and bring in the calculator to start doing our computations. So we have that negative 0.226. We have to give ourselves some margin of error, so let's see how much margin of error we need. So 1.697 times 1.8203 divided by the square root of n. Match the number of decimals here with the number here. We have 3 decimals, so we'll put 3 decimals, 0.555. And then we want to do the subtraction and the addition. So if we subtract, let's see, negative 0.226 minus 0.555, we get negative 0.781, and if we add, we get 0.329. And then what is it that we're supposed to write as an element of this interval? So we are supposed to be computing a 90% confidence interval for the difference in average sales before and after. So the sales before would be mu1, the sales after would be mu2, and they want the difference between those two. So we're 90% confident that the difference in those sales is somewhere in this range, from negative 0.781 to 0.329. So now we've computed it, but we really want to start thinking about, alright, so what does that mean? What does it mean that the difference could be negative or the difference could be positive? Well, if the difference is negative, that means mu2 is bigger than mu1 by 7.781 units sold, because a negative comes out of a subtraction anytime the second number is the bigger number. But if that difference is positive 0.329, that means that after the plan, the sales would be smaller than before the plan by 0.329 units. So we've got kind of a big range in possibilities for what could be going on here. This number over here indicates that the sales could have gotten better by almost a full unit more sold per person, and this right here indicates that the sales could have actually gotten worse, because again, when does the difference come out positive? When does the subtraction come out positive? when the second number is lower than the first one, and this is after the plan. So if we're getting a positive, that's saying maybe the average after the plan is actually even worse than it was before. So this is our, I think, trickiest type to interpret when it has a negative and a positive range. I'm going to go ahead and interpret it all from the point of view of mu2, which is after the plan. And I'm going to look at the bad side. Maybe things have gotten worse by 0.329 units per person. Maybe the sales have gotten better by as much as 0.781 units per person. So let's see if we can write that out down here. So interpret the interval in terms of the application. I'm 90% confident that the true mean sales after the plan was enacted, so that's from this point of view, is somewhere between, and I'm going to start off with this number right here, 0.329, and again, that means that the sales after were less than this by that amount. So I'm going to say it's somewhere between 0.329 less units sold, and then on the other side, 0.781 units, more units sold. And I'm going to put more there because in order for a subtraction to come out negative, the second number needs to be bigger. So this difference being somewhere in this range means that there's a lot of mystery really in how sales are going. It could be anywhere between 0.329 less units sold and 0.781 more units sold than before the plan was enacted. So are we seeing more sales? Maybe. Are we seeing less sales? Maybe. Is it possible that things didn't change? Yeah, because zero's in there too, and that would indicate no change. So let's go ahead and follow up on that by looking at part E. Explain how this interval that we just computed in part C agrees with the decision we reached in our hypothesis test back in part A. So I'm going to start out by writing the interval down, just copying from up here. So if mu1 minus mu2 is somewhere in this interval, and we are 90% confident that it's in there, so I'm going to start off with that hypothetical. If the difference is in here, what does that imply? Well, one of the things it implies is that mu1 minus mu2 could be 0. And I say that because 0 is in this range. When we do a confidence interval, anything in that range of numbers is a reasonable possibility for what this answer could be. And if the range goes from a negative to a positive, then it has to include 0. And let's suppose it was 0. What would that mean? Why does the subtraction come out to be 0? Only if these two things are equal. So that implies to me that mu1 could be equal to mu2. I don't know if it is or if it isn't equal, but that's definitely a reasonable possibility. And then I think back about, well, what did H0 say? And H0 said that mu1 was equal to mu2. So is that true or is that false? Well, if they could be equal, then this could be true. And then we just have to think back to the idea of hypothesis testing. If HO could be a true claim, should we reject it? And the answer is no. We would want to reject HO when we're confident that it's false, but not when it's reasonable that it could be true. So I would end up saying, do not reject HO. And then, does that really agree with our decision from the hypothesis test? Well, we can pull that page back in and say, yes, that was our decision, do not reject. So from the point of view of the confidence interval, why didn't we reject HO? Well, because if we get a confidence interval like this, which I've copied down here, then since 0 is in that interval, that means the difference could be 0. And if the difference is 0, that only happens because mu1 is equal to mu2. And that was what HO was claiming. So our interval is making it a reasonable possibility that HO is a true claim, and we don't want to reject a claim that has a reasonable shot at being true. Again, we only want to reject HO if we're confident it's false, but our own interval allows for the possibility that it's true. So we're going to play it safe, not take the risk of a type 1 error, and do not reject HO. Alright, that wraps up our extra example from section 11.1.